Hi students, in the second video for online lecture 6, we are now going to introduce the electron configuration. So an electron configuration is how the electrons are distributed among the various atomic orbitals in an atom. We have done this previously by using the quantum numbers. But because the quantum numbers can take some time, we are wanting a little bit more of a shorthand so we know a predictable location for our electrons. So we can state that an electron configuration contains three parts. The first is the principal quantum number. Notice that that starts in the first position. So our n value that we saw previously during our Rydberg equation, as well as during our quantum numbers, is located as the numeric out front. Then we get the angular momentum quantum number, L, as the alpha part, telling us what orbital type we have. Finally, the number of electrons in an orbital or subshell is placed in the upper right-hand corner as a superscript. This means that we are going to put in the exact number of electrons that we have without breaking the rules that we've seen previously. So we must know the top end numbers of our orbitals and subshells. The reason that we do this is that our electron configuration is a shorthand of not only our quantum numbers, but an orbital diagram. As you can see here with our example, we can write the electron configuration as 1s1, or we can picture this as a little box for our 1s orbital with one upward arrow. It is going to take us a lot of time to write orbital diagrams or our quantum numbers, while the electron configurations are much more simple once we get a flow going of how we are going to do this. When it comes to the electron configuration, you are going to want to follow your quantum numbers as well as the periodic table atomic number in order to fill your orbitals and subshells correctly. So let's look at a couple of examples. First and foremost, let's look at phosphorus. Notice that I am going to fill the 1s orbital first. I am allowed 2 electrons in that orbital, so that is why I'm allowed 1s2. Electrons 3 and 4 now must go and populate a higher subshell, that being the 2s2. Notice that I am only allowed to put 2 in that location. This gives us 4 total electrons. For our 2p subshell, notice that I have 3 equivalent orbitals that are allowed 2 electrons. This is why we are allowed to only have 2p6, giving us 10 electrons. If we go and add the next 2 electrons, that is going to be in the 3s orbital. And then finally, when we get to phosphorus, which only has 15 electrons, notice that our last 3 electrons go in the 3p subshell, 1 electron in each of the degenerate orbitals. This is a good full electron configuration. For potassium, notice that our first 4 subshells are the same. That includes the 1s2, 2s2, 2p6, 3s2. But because potassium has more electrons than phosphorus, we are able to fill the 3p subshell completely to a maximum of 6 electrons. Finally, for our last electron, we must go and put it into the 4s subshell, which was previously unoccupied, and you will see that with the 4s1. You are expected to be able to do at least one full electron configuration on an exam. This means being able to not only do the principal quantum numbers as regular numerics, putting in the subshell based off of the alpha, and getting the correct number as our exponents for our electrons. You can only put as many electrons in that you have, and you cannot go and put too many electrons in a subshell. Now, this is nice and all, but if we start getting very deep into the periodic table beyond element 50, the first 50 electrons are highly predictable, and we would be repeating the same steps over and over as of writing 1s2, 2s2, 2p6, 3s2, and that can be very cumbersome. So let us go and do the shorthand to the shorthand of the shorthand of our Schrodinger equation. And that last shorthand is commonly called the noble gas notation. This means that if you pass a noble gas, you are able to put it into brackets. So this is incredibly helpful for us, as that once we get to a noble gas, that does not mean if you stop at the noble gas, you are allowed to put that in brackets. But if you get to it and go beyond it, that is just like saving a video game or trying to pick up your progress with a puzzle by leaving it as is. So in the case of argon, you will see that I have 1s2, 2s2, 2p6, 3s2, 3p6. Once I get to that position, I am able to put in argon as my save point. So that way, if I were to go back to my potassium, notice that potassium is just one electron beyond that. So I would be able to state that this should be argon 4s2. Now, as you can see here with calcium, which is the next atom in line after potassium, I am now going to fill the 4s orbital by adding the second electron, and that is how I get the shorthand notation. On exams and quizzes and in problems, if it asks for the full electron configuration, you are expected to give each individual subshell. If it asks for the noble gas notation, you are free to use the noble gas in the bracket as you see fit. One of the issues that comes up with electron configurations is trying to understand a predictable fill pattern. One of the things about it is that we now must talk about the stability of our shells and subshells, not only because of the electronic moment, but because of the magnetic moment that we talked about previously in the last video. So what we're going to find out is that a full subshell is actually incredibly stable. So what we might mean by that is if I go and claim that this is the 2p subshell, that means that I have all of my electrons full and they are paired up equally. An empty subshell, however, is if we go and look at something like if I were to go and have the 3s orbital. There are many atoms that have empty orbitals, and they do not affect the electronic or magnetic properties of an atom. So if we have a full subshell, that is wonderful. If we have an empty subshell, that is fine as well. One of the things that we have to be very concerned about is typically what we call our half-filled subshell. So if I go back and let's say I will go and do a 2p orbital in this case as an example, this means that I have one electron in each orbital going and being placed in there all with the same spin. In some textbooks, they will call the half-filled subshells Hund's compliant, because this means that we have as many electrons in there before we go and pair up our electrons. So if I were to go and look at, let's say, the 3D, we know that there are 5 orbitals in that case. And now I would have 1, 2, 3, 4, and 5 electrons in that subshell. So we have full, we have empty, half-filled are fairly stable and can be predicted in many cases. The worst case scenario is what we call partially filled. These are any combination of electron pairing in which we do not have a balance. So one way we can look at that is if I were to go to my 3D subshell and go in and put 2 more electrons. So notice that I have 2 that are paired and 3 that are not. This is considered partial. So if I go back up to my 2p, this would be considered partial as well, because now I have 1 unpaired electron in that final orbital. These are the worst because there's an imbalance in the magnetic field of these electrons, and it starts to perturb the volumes and the spaces that we are in. Some atoms go and account for this, even though they don't follow the order that we're used to seeing. We call these the anomalous series. Anomalous meaning don't follow normal trends. So let's go ahead and look at copper. Here, I have what is the periodic table filling order with the correct number of electrons. But notice that I have here as 4s orbital, and if I draw in my 3d orbital, I will go ahead and get my 5 orbitals. I would have 1, 2, 3, 4, 5, 6, 7, and you'll notice that I fill this up to my 3d9. But the problem here happens to be this electron right here. He is perturbing the 3d subshell. So what will happen is that currently I have a full subshell, and here this is claimed to be partially filled. What can I do? Well, this energy difference here between the 4s and the 3d is so small that I am able to move one electron from my 4s orbital and place it into this 3d last orbital, and you can now see what I will get. So if I go here and say I have 4s, I now only have 1. But now for my 3d, let me draw in my orbitals. You will now notice that I have all 10 electrons in my subshell. So now what I have done is I have a half filled subshell, which is less stable than a full subshell. But by that donation of the electron, I am now able to get a full subshell as well. So as you can see for copper, I went from a full and a partial to a half and a full. This makes this much more stable. The transitions you really want to look for as you're starting to do these is you are going to look for S to D transitions in which you can normally move one electron. There is only one atom that is known to do a 2-electron move. And then finally, what will happen many times is the D to F transitions. If we are able to move one electron, trying to help us with stability, this is going to benefit us. So when dealing with the anomalous series, anomalous means it doesn't follow the rules. So you're not going to do this for every single one of our atoms. Most of them are going to follow a very predictable order. But if something just doesn't seem right, or if you are able to look at your subshells and say, if I move one electron, I can gain stability, you are going to want to do this. So here are the known electron configurations. Notice that I give you the ending configurations for the first 112 atoms. You are not expected to memorize these. But what will benefit us in here is that as you're starting to work through examples, always have this sheet in front of you so that way you can compare and make sure that you are getting the same electron configurations. If you get something that's slightly different, you might be able to see that you are getting a species that's in the anomalous series. So what can we do with the periodic table and the electron configuration? We organize the periodic table based off of the last electron going in. So as you can see here, the S1 electrons are all located in our alkali metal series. So regardless of whether we have sodium, which is a 3s1, or let's say cesium, which is 6s1, the last term is always an S1. When we go to our alkaline earth metals, notice that we have a full S subshell by doing this with S2. Then when we go to the boron group, notice that I have S2, and then with the same principal quantum, I have a P1. These now have populated the p orbital set of that same principal quantum number. As I go to carbon, notice that it's P2, nitrogen is P3, oxygen is P4, and the reason that our halogens are so reactive is notice that it is S2, P5. P5 means we need one electron to become like that of the noble gases, so we are going to gain many electrons, typically one of them, so that we can get to our P6 and we will start to get some electronic stability. As you see here with our d orbitals, notice that they are D1. But another thing of the electron configuration is notice that scandium starts in row 4, but is actually 3D. So when dealing with our transition metals, we need to go with what we typically call the N-1 rule. So for our transition metals, we need to get rid of one of our principal quantum numbers. So for our transition metals, we are going to go and have the N-1 rule. So this is going to be D1. Then we go to D5, which is our Hund's compliant, which means that our chromium group right here is very well known for being part of the anomalous series. Then I go to D10, which is zinc, cadmium, and mercury, but that also means that we have to worry about our copper group here because they could also be anomalous series as well. As you look here, we go to the 4 Fs, but notice where they're supposed to be placed. Our 57th element and our 72nd element are located here. That means that our 4 Fs should fit in there, but it's technically in row 6. For our rare earth elements located at the bottom, we must now not go by the N-1 rule. For our rare earths, we are now going to go N-2. So this means that as we are going down and picking up those electrons, if we're in the 6th row, it's really the 4 Fs. If we go to the 7th row, it's actually the 5 Fs. This is going to help you immensely as we are starting to go and do our electron configurations. So there you see the 5 Fs, even though that it is in the 7th row. So let's try a couple of examples of trying to determine our electron configurations. So the first one we want to do is sulfur. So what I will do here is look at my periodic table. Here is row 1, here is row 2, and here is row 3. So now what I need to do is go and get the first 2 electrons filled in this periodic table. So this would be electrons 1 and number 2. Those are incorporated in my 1s2. So then I need to go and get electrons 3 and 4. So that can be done by 2s2. Notice that I will make the jump across the transition metals to get numbers 5 through 10. Well, what orbital set is that? Well, that is going to be my 2p subshell. And notice that there are 6 electrons in that group. So that has now given us the first 10 of our species. So what happens with numbers 11 and number 12? Well, that is now the 3s. So here is my 3s2. And notice that I need electrons 13, 14, 15, and number 16 is going to give me sulfur. So I only need 4 more electrons. This is done in my 3p subshell. And because I need 4, I will just put the 4. And this is the correct ground state electron configuration for sulfur. Now let us go and look at palladium, which you now see labeled on my periodic table. So the nice part about it is that most of this configuration is going to be the same until we get to the very, very end. So what I can do is go in and fill in all the way to sulfur and then start to extend past it. So for my sulfur, I had 1s2, 2s2, 2p6, 3s2, and before I had only 4 electrons, but because palladium has much more than that, we are now needing electrons 17 and 18. So now I have a full 3p, so that is going to be 3p6. So what can I do now? Well, notice I am in row 4. So that means that I need 4s2. That gets me electrons 19 and 20. But now electron 21 is in a new block. This is the transition metals, and I'm expected to go and put them in using the N-1 rule. So that becomes 3d10. Once I get through all of those electrons, that getting me up to 30, I now need to get electrons 31 through 36. Well, that is back in the 4p subshell, so that is going to be 4p 6. So now I need to get electrons number 37 and 38. Now I'm in row 5. So if I do that, that should be 5s2. And you'll notice if I go to palladium, I will end up getting 4d8. This should be the standard fill order. However, let's look in where it says that palladium is diamagnetic. That means that this group here must be fully paired. As you'll notice, it isn't. So palladium is the only known species to do a 2-electron move. This is part of the anomalous series. We are going to take our 5s2 electrons and put them in to fill up my 4d subshell. So the correct order actually in here will now read as 4d10. So when doing this, you would be able to write your standard electron configuration, see that it is wrong, and be able to change it from there. This is incredibly helpful for us as we're starting to go along. Once again, follow the fill order of the periodic table, and then if you are given an indication of being anomalous, make sure that you account for that. So let us try this final example for ruthenium. What is the correct electron configuration for ruthenium? It's very important that you go and look at your periodic table to see where it is on your periodic table. So as you're going through, in the transition metals, in B6, you will find ruthenium. If that is the case, you will come to find out that it is krypton, which is the noble gas previously before, 5s2, and because it has only 6 electrons in the d orbital subshell, this is going to be answer D. Make sure that you know your identification of your elements and then start to build through each atomic number to get there. Getting the wrong element will give you the wrong electron configuration. In this video, you saw a few examples of how electron configurations can now be very predictable based on the fill order of our species. In the next video, you are going to see that how we are going to add more electrons in the case of an anion, or in the case of a cation, a positively charged ion, how we are going to take away. Have a great day.